Yes. Right. Good afternoon, everyone. Am I audible to everyone in the back? Great. So, I'm going to talk about what axial flux motors are, what the underlying technology behind the axial flux motors is, and what benefits it has, especially at the system level. Our customers are OEMs and system integrators, so I want to highlight the benefits that they'll have in order to make the sale to them more viable. Also want to talk about the global markets for axial flux motors and how we want to scale the axial flux motor technology. One of the impressions is that it's a prototype and niche product, suitable for high volume, high performance applications, but not quite at the cost range. That is something that we're consciously trying to change at Turntide. So just a bit of history about Turntide. We were formed in 2021, the Turntide Transport Division, by taking 3 companies in the northeast of England together. Sebcon, which was a power electronics manufacturer with a long history, iVT Technologies, which is the axial flux motor manufacturer, and Hyperdrive, which is the battery manufacturer. The idea of bringing all these 3 technologies together was to have a one-stop shop for your powertrain needs. Some of the markets that we serve in and why axial flux motors are suitable in those. There are a lot of space constraints in the off-highway vehicle sector. So construction and off-highway vehicles, especially the ones that are hybridizing or just moving to the 2nd and 3rd generation of their electrification journey, tend to have a lot of space constraints. That's where the compact axial length of motors makes it very suitable. Premium automotive is another segment where performance is constantly in demand. No matter how much torque or power delivery you have, the automotive sector always wants more in a smaller form factor, as mentioned by some of the other speakers as well. Bus and truck, although there are no space constraints there, the high torque demand by those large vehicles make the axial flux motor suitable as well. Marine is another sector where hybridization is quite popular. So conversion of the ICE vehicles into hybrid engines with axial flux slotted in a P2 hybrid configuration is very suitable as well. And light rail and trams are another sector where the axial flux motor technology are very beneficial. We'll go through the electric motor classification. Most of you, I'm sure, are familiar with different electric motors and their pros and cons. But as far as AC motors are concerned, the induction motors have been very popular for many decades. The higher efficiency needs of the industry keep pushing the induction motor design to be better, but there's an upper limit of 85 to 90%, beyond which you're not able to get induction motors any more efficient. So enters the synchronous machines. 3-phase permanent magnet motors are the ones that are having the highest performance in terms of power density, torque density, and efficiency, and that's the space that we tend to play in. There's more niche synchronous and switch reluctance motors. If your performance requirements are not extreme, then those tend to play well, especially from a cost perspective. But if you have high performance demands and efficiency demands, then PMSMs are the way to go typically. So, just a survey. Can anyone guess when axial flux motors were invented? A range, year, decade?
1984.
1930.
About 100 years before that?
Yep.
So, the first motor by Michael Faraday in 1821 was an axial flux motor. The radial flux motors were developed a few years later by Thomas Davenport. So that's a diagram of Faraday's axial flux motor, and the later model of the Faraday's axial flux motor looks more like the pancake design that we see today. So what is an axial flux motor? The direction of the magnetic flux determines the topology. In a radial flux motor, the direction is radiating out from the axis of rotation, and the magnetic arrangement in the axial flux motors mean that the direction of flux is between the magnets axial to the axis of rotation. One of the key determinants of torque and power delivery is the strength of the magnetic field. If the magnetic flux path is shorter, you'll have higher magnetic field strength. Also, if the diameter of the rotor, which is directly proportional to the amount of magnetic material you have, is bigger, you'll have a greater magnetic flux strength. So the key determinant becomes the D2L ratio. Higher the D2L ratio, greater magnetic strength, lower magnetic flux path, better overall efficiency and torque delivery. So in terms of axial topologies, the D2L ratios tend to be very high, and that's what makes it that much more torque dense and power dense and more efficient. So what you tend to see is, compared to a standard radial flux motor, the axial flux motors are 2 to 4 times more torque and power dense. What this means is you'll see at least 50% reduction in weight and volume if you want to go for the same form factor, if you want to go for the same power delivery, or vice versa, you can have twice the power and torque delivery for the same form factor. So at the system level, for every 10% reduction in vehicle weight, you can improve the range by 13 to 14%. So with our axial flux motors, another advantage you have is a reduction of the gearing ratio, because they tend to operate in a high torque, low speed environment. So if you're using a 1:9 gearing ratio, you can go down to 1:6 or 1:4 gearing ratio, thereby reducing your gearing weight as well. Both those factors mean a lower vehicle weight, a higher vehicle range, and therefore a lower total cost of ownership. This is the pitch that resonates most with our OEM customers. One more benefit is low or no cogging torque. So depending on the stator construction of radial flux motors and some axial flux motors as well, you tend to see a lot of cogging torque and torque ripple. If the stator construction in axial flux motor is done in such a way that there's no segmentation, then you get no cogging torque and a very smooth delivery and operation. That's one of the highlights of our motors as well. We've designed the stators such that there's low torque ripple and no cogging torque. Even within axial flux motors, there's a lot of topologies. The one that we tend to go for is the double stator single rotor or the Canon type. So I've got the two main popular topologies on the diagram here. The one on the left is the dual stator single rotor topology. One on the right is the dual rotor single stator topology. Depending on the permanent magnet structure you want and how much efficiency you want to get out of the magnetic material, you can select either. If you have freedom of getting more magnetic material, you're not cost prohibitive, the dual rotor single stator topology is the one to go for. If cost is king, which it is for high volume applications, then the DSSR technology tends to work better. We've designed the motors using a lot of simulation. Here are some diagrams of the electromagnetic CFD and FEA simulations that we've done. We've done all of those simulations to ensure that the cooling circuits are designed perfectly, that the EMAG design is optimized, the slot hole combinations are optimized, and overall stator and rotor construction is such that it's a very robust and durable design. So just an exploded view of the motors. We've got a high voltage top box connector at the top, a spider cage arrangement of magnets in the rotor at the center, 2 stators on either side, and a water ethylene glycol supported cooling jacket, which does the cooling of the motors. So what is the end value proposition? It enables much higher torque and power delivery in a very thin design. So it becomes the motor of choice for space-constrained applications. Also, if you want higher performance and you're not space-constrained, that still gives you the same benefit. Another key benefit is the design scalability and modularity and flexibility. These motors are stackable. So you can, along the axial length, you can stack multiple motors and get higher power and torque ranges. The IE5 efficiency class is one being defined recently. These motors meet the IE5 efficiency class and higher, so peak efficiency is more than 96% if tuned correctly with the inverter. I'll have that caveat in there. And cooling with the standard cooling mixture like water ethylene glycol, so that you can share the cooling circuit with power electronics as well. This is the full range. I'll just explain the nomenclature in here. The first number is the number of stacks. So the 125, 30, 40, and 143 are single stack motors, starting from 60 kilowatt nominal power all the way to 110 kilowatt nominal power. You can take 2 of the 130s, stacked side by side, and you get an AF230, so that's a double stack motor. Our current designs support stacking up to 4 motors together, so at 376 kilowatt, you've got an AF440 motor. As you go up in size, you tend to go down in speed. So given the higher inertia of the bigger sized motors, you you tend to go down in speed. That also supports the high torque, low speed operation and the gearing efficiencies that come with the high torque, low speed operation. If you look at the weights on there, you can compare with the radial counterparts. You can get 60 kilowatt out of 22 kilograms at the smallest range. Compare it to radial flux motors are typically 40 to 60 kilograms in weight. So what are the improvements that we are making? We've got a very strong simulation-driven design. We do very strong FEA analysis on all our components, cooling channel optimization using the best-in-class computational fluid dynamics tool suites, full assembly thermal FEA as well, and electromagnetic FEA. We want to support high-volume manufacturing as well. One of the complaints with Axial Flux Technologies is that it's not scaled for high-volume manufacturing. That is something that we're actively working on changing by having high-volume component tooling and insourcing a lot of the processes as well, so that it's automated and optimized. The housing is also fully designed for manufactured to support high volume tooling, and it's ruggedized to ISO 16750 standards. So for full automotive use, the highest classes of ISO 16750 are tested using these motors. And we have a whole range of shaft designs as well to make it scalable and suitable for different shaft and spline geometries. Premium automotive, traction is one of the most attractive applications. So for supercars and hypercars, ranging from 150 kilowatt to 250 kilowatt front and rear drivetrain units, these motors are very popular. On highway and off-highway commercial trucks and buses, we've got applications like electric power takeoff and the three power classes of 25, 50, and 100 kilowatts, and various ancillary applications such as BEV and hybrid truck fans and cooling pumps as well. A very interesting application is fuel cell superchargers. So the smaller variants of our motors that run at 12,000 RPM are especially used for fuel cell superchargers as well. In off-highway, it's suitable for not only track and wheel traction, but also ancillary functions such as slew and swing. It's also found applications in street sweepers, both for traction and various implements. And the rugged nature of it also makes it suitable for all-terrain vehicles. Some of the more exploratory markets where we see a slightly longer trend for electrification or longer ramp to electrification, like aerospace, eVTOL, also have axial flux motor technology to thank for because of their high gravimetric torque density. So the lightweight nature required in those industries is supported by these motors as well. Marine, as I mentioned, is a very popular application. We are working with a few major OEMs in the space to electrify the marine platforms, and rail is another popular end application as well. So what I want to conclude with is that they're inherently superior in terms of their design and torque and power delivery. They're lighter, more efficient, and more powerful motors, and that we are leading our way in terms of making that scalable and high volume manufacturer friendly. Happy to take any questions.
Good question. So they're smaller, lighter, higher power. What's the cost delta?
Yeah, so the general perception on axial flux motors is that it's 2 to 4 times more torque dense, but also 2 to 4 times pricier. We are bringing the price at parity with radial motors now, with our next generation of motors. So we are opening up the competition, and we are sure to secure some of the radial flux motor market share by bringing it at price parity with it. Why wouldn't you want a higher performance at the same price? And that's the thesis that we're working on. So thanks for that question.
Wondering what kind of sensor technology you use with the motor?
Resolvers and encoders, you mean position sensors?
Yes.
Yeah, so we've got temperature sensors for stator and rotor temperature, bearing temperature as well. Usually PT100s or PT1000s, and we use sine cos or UVW resolvers and encoders.
So also they're higher torque. I mean, in my experience, the axial flux motors are higher torque and much more compact. But at the same time, they're kind of deliver that torque at lower speed, really typically. So the reduction ratios are much lower, but at the same time, the speed often doesn't go above sort of the constant torque, base speed, essentially, isn't it? Or is it possible, that's kind of what I'm getting at, is it possible to push axial flux motors beyond that? Is that an electrical limit, is that a mechanical limit, or is it just a not worth it limit because it's so powerful?
So the torque speed characteristics for the motors are no different to the radial ones.
Yeah,
But with the higher inertia, you tend to be able to operate it at high torque and low speed, therefore reducing the bearing ratio required.
yeah, okay.
But nothing that makes it different from the normal knee curve or torque speed characteristics that you get. And the field weakening that you do for radial flux is the same as the field weakening that you would do for axial flux.
Okay, that's what it's just strange because the field weakening, I don't see a lot of axial flux motors operating in that field where they tend to be kind of.
So for superchargers, for example, that do require that higher speed operation, we do go into field weakening operation as well. Any other questions? No, thank you for your time. I hope this was useful. Thank you very much.